Hello, we are ECE Group 14, Human Initiated Casualty Detection/Response System. My name is Darren, and today I am joined by Vanessa, Tyler, John, and Greg.
Our project is a system to improve the engineering spaces on board naval ships. Any fault that occurs within these spaces are called casualties. The severity of these casualties can range from an operational shutdown to loss of life. Managing and mitigating these casualties takes time, and responders must secure the area before starting the procedures for that event. Currently, the system in place alerts the crew to deviations from allowable constraints from certain sensors. We want to decrease the time to identifying that a casualty has occurred and provide assistance into identifying and responding to the type of casualty that has occurred. Our problem statement is the goal of this project is to develop a casualty control system which helps automate elements of the system in real time through the implementation of a human-initiated step-by-step mitigation procedure. The most crucial part of any diesel-operated ship is the turbine. It's used for power generation and locomotion. The three primary casualties associated with this lube oil system are loss of lube oil pressure, a major lube oil leak, and a hot bearing. These system failures can cause damage to the journal and thrust bearings, which are instrumental in smooth operation of that system.
While designing this system, there were certain constraints we needed to follow for proper software integration. The software must allow high-speed data transfer between the sensors, master server, and human-machine interface, but also facilitate reliable delivery of casualty response mechanisms. To achieve fast data transfer, UDP was chosen due to its low network overhead. Since these packets will be transmitted many times per second and over Ethernet, reliability concerns with UDP are minimal. Commands sent from the HMI to respond to a casualty will be sent over TCP. This protocol ensures our commands are delivered properly to the server and sensors.
For our project, we decided to focus on lube oil systems. If lube oil fails suddenly, then damage can occur to the shaft and/or the bearing. Replacement will be required. An issue that can occur with the lube oil system is a loss of pressure, which can cause the film of oil between the shaft and the shoes or pads to disappear or shrink, causing damage. The other primary issue is the outlet oil temperature raising too high, which can cause a reduction in the viscosity of the oil. This causes the shaft to contact a bearing, shoe, or pad and causes damage. The team focused on loss of lube oil pressure and the major lube oil leak.
The problem was solved by building a prototype of a lube oil system that interacts with the Human-Initiated Casualty Control System via a graphical user interface, or GUI. The GUI is able to report the casualty's general location, as well as initiate a response to the casualty through a human-initiated procedure built into the DAU and carried out by the control system.
This prototype has inlaid sensors for temperature, pressure, and flow rate. There were also servo-operated shutoff valves in place to replicate blockages/leaks to test our system and to make sure it could detect those issues accordingly. The physical system was a continuous flow line that consisted of a sump to a pump, to a filter, to heat exchanger, to a load with sensors laid out in between the necessary components.
In order to follow proper software production and system design processes, the pseudocode pictured here was developed. As one can see, this pseudocode encompasses not only one aspect of the system, but all three programs, and describes the interactions between them. After initialization, the system will utilize the traditional control system to collect sensor data and relay an update message to the DAU, or Data Acquisition Unit. The DAU then processes the data, determines the presence of alarm states and casualties. It then updates the GUI, which is also known as a human-machine interface, with the current sensor data. The human-machine interface will prompt the user for action if a casualty is detected. Once an action is initiated by the user, the DAU will compile the appropriate instruction and send it to an appropriate microcontroller in the traditional control system. That microcontroller will then execute the actions described and send an acknowledgement to the completion. In order to monitor and control such a detailed physical system efficiently and reliably, the team settled on implementing a distributed control system. Pictured above is the zone division of the physical system. This is to say that each color represents a different area of the system that is monitored and controlled by a separate microcontroller. While dividing the system into different zones and allowing each to have its own controller made the actual execution of duties more efficient, it presented a new issue in how the controllers would apply controls and relay their information to the DAU. To solve the communication issue, the above controller schematic was developed. It prescribes not only the placement and intercommunication of each controller, but also the controls that are to be operated from each. The communication issue was solved via the implemented I2C bus. A separate controller responsible for compiling and sending the system status message to the DAU would poll each controller for a separate update using this I2C bus. Once the polling routine was completed, the message would be sent to the DAU. The DAU would then determine a response, which it would send to the implemented casualty response controller. This controller would unpack the response, interpret the message, and set the appropriate hardware controls. These hardware controls would activate the appropriate interrupt routines in the zone controllers, which operate a specific piece of equipment.
The GUI is broken down into 5 sections for monitoring each of the 5 zones of the mock lube oil system. The GUI will display the sensor data that it gets from the server. For each of the zones, M will also display a warning if one of the thresholds, as defined in the EOCCs, is exceeded. Once a warning has been displayed, the user will be told what went wrong and how to respond to the error. Now, whether the user goes and fixes the casualty themselves, or the system can fix it automatically and the user just needs to sign off on what the system will do, that is up to the user itself to read the error and see how to respond accordingly. The economic impact of our project is twofold. 1. The automation of the casualty response system will allow responses that are both faster and safer for naval vessels. Therefore, it will bring the cost down related to injuries and maintenance. The second economic impact is a reduction in shipping cost if the project is used for commercial applications. This is a compounding effect of the first impact, as businesses will save costs elsewhere and be able to reduce the prices of their products. The social impact of our project will come as a benefit that the workers will reap from the increased automation. With our project implemented, workers should feel a lightened load on their work and thus have reduced stress level at their job. And they will also have time to do more work that would have otherwise fallen into a low priority category.
From an environmental standpoint, current naval vessels are at risk of leaking dangerous contents into our oceans in the event of mechanical failure. Our system aims to reduce the duration of mechanical failures, preventing leaks, and save on material waste by identifying potential maintenance problems sooner. Ethically, our system will enable naval vessels to have less human casualties, and this will save lives. To achieve our software integration, we relied on several standards for data transfer. The IEEE 802.3 standard for Ethernet helped us navigate the problem of sending sensor data from our sender/receiver nodes to the central server, and from the server to the human-machine interface. For inter-sensor node communication, the UM10204 I2C bus revision 6 was our go-to. Lastly, for the transport layer protocols mentioned in our background, RFCs 793 and 768 for TCP and UDP respectively were utilized as references.
The physical portion of the project is mostly complete, as the tubing is fully attached to the components that allow for a closed loop system of a mock oil lube system that would be present in naval vessels. The sump and the pump are also attached so that the system can push liquid throughout the mock oil lube system. The load for the physical portion of the project, however, is missing, and this is due to the fact that there were many delays from the company that was distributing the load that the team bought. There was not enough time to buy a new load that could be implemented into the project before the COVID-19 interruption had occurred. For the overall progress in regards to the sensor and zone controller code, the flow and pressure sensors have been programmed in order to pull data from the mock lube oil system. In regards to the temperature sensor, there was a hang-up in which an op-amp was required to properly pull data from the physical system. However, this part was not ordered before the COVID interruption had happened. The flow sensor was simple enough. It is just using a simple analog read to grab the flow data in liters from the physical sensor system. The pressure sensor originally gave its data in units of pascals, so a little code was added to convert the units to psi. The zone controller was then programmed to pull data from the sensors and marshal the data into a packet architecture that the team created. The architecture in this case is just designed so that the first 4 bits of the packet are the zone and controller ID, and the last 24 bits are the sensor data, which is then delivered to the server for further processing.
We were able to implement a server using C# and .NET Core to receive sensor data from our master sender node. The server is also able to communicate with the human-machine interface. We chose to utilize .NET Core for its cross-platform capabilities and our knowledge of C#. Our server code used the sensor packet architecture from the previous slide to handle the packets. The HMI is able to receive data updates from the server and display it to the user.
Due to the COVID-19 pandemic, the project will have to be left in an incomplete state, where most of the components to complete the project have been put into place, but there is no time for debugging, tweaks, and testing. The pieces for the hardware section of the project have been mostly complete, with the sensors attached. However, the controllers still need to be set up, and the load needs to be ordered and attached. The software for controllers, GUI, and server are mostly complete, with some debugging needed and integration into the physical aspect of the project. Our revised scope, therefore, is just to document the work that has been completed and create a plan for moving forward should the work be picked up in the future by another senior design group.
Here is the final updated timeline for spring term. As mentioned earlier, with the change of scope, the spring term was cut short, so all that could be done was the papers and the online presentation. Here is the team member responsibility. Each person contributed to the overall success of the project. Darren worked on the network implementation for the server and the Arduino side, as well as the GUI. I myself worked on assisting John in building the physical prototype, coding the valves to open and close, and working with the team to complete all the documents needed and to make sure everyone was staying on top of the work they needed to do. Tyler worked on defining equipment and network boundaries, setting up preliminary message structure, defining controller placement and function, as well as external controls to be routed from the response controller. He also helped design and implement the I2C bus and polling routines to be utilized by the zone controllers and information clients. John worked on designing, budgeting, and setting up a physical prototype to replicate a lube oil system. Greg worked on posting updates to our project on Instagram, as well as programming for the sensors, and he worked with Darren to ensure that the controllers could send the data to the server. This was our budget for the project and all the parts that were purchased. The total shown on the slide is $522.86. This is different than our Pat Doer Fund requests because of COVID-19. So 2 of the major parts were unable to be purchased to continue with the project. For our project, we have received many questions. Here are some of them now. The first one is, what is the purpose of this project? The purpose of our project is to analyze efficient network traffic protocol and develop testing methods to make sure the prototype aided and showcased the goals of this team. Our second question is, what is a casualty when referring to engineering spaces? A casualty is any machine or system fault. Our next question is, what documents are we using to govern our system actions? The documents that are used are Engineering Operation Casualty Control Procedures. These are naval documentation on how to deal with engineering casualties. Our fourth question is, why did you choose a lube oil system? The reason we chose a lube oil system is because the crucial component for power generation and locomotion on board a ship is the lube oil system. The final question is, does this project apply to lube oil systems only? No, this is not the case. The purpose of this project is to prove the concept as a whole. Once the concept is shown to be viable, automated procedures for casualty interference and recovery can be developed and implemented for any of the other systems located in these engineering spaces. Some of the other questions we have received are, why did you choose this as a project? This project was chosen to remove the responders from this procedure, ultimately removing the unnecessary damage posed to life and machinery present in the current casualty response process. Another question we have received is, why was everything split up into multiple zones? The physical system was divided into zones to more closely resemble a real engineering space, where all of the equipment is directly connected to a local data acquisition unit, or DAU, or in this case, the zone controllers that apply local controls and transmit the data to other systems. Another question was, why choose I2C as your serial protocol? The main thing this project needed is its inter-controller communications was to be a reliability. I2C allowed the designers to be confident the data exchanged on the serial bus is valid through its use of the acknowledgement bits, or ACK. It also allowed us the ability to easily request data from individual zone controllers rather than just trying to grab data off of a line. Another question was, why did you choose to write the server in C#? The language was chosen because .NET Core allows write once functionality and is the language Darren and Greg have decided are the most comfortable in. The last question is, why did you choose the packet structure? We wanted to minimize network traffic, so we explored bit packing as our solution. Here's the final list of questions that we have received. Why was the GUI written in C#? The GUI was written in C# because Visual Studio has best in-class tools for creating interactive GUIs. Another question was, did you ever have issues with the technical stack that you chose? Yes, we did have issues. Initially, for the TCP server and for the GUI, we were going to use Python. But after a discussion, we found that one of the team members had a larger knowledge base of using C#. Another question was, why do you have only 2 Arduinos receiving and sending data to the server? The reason we only have 2 Arduinos sending and receiving data to the server is in order to save on the cost. The final question was, why TCP over UDP? TCP stands for Transmission Control Protocol, and UDP stands for User Datagram Protocol. We use TCP to ensure that no packets are dropped, and all our data makes it to the server.